All right, hello everybody. Welcome to CSM 61B exam 2 review session. For the interest of time, let's just jump straight into the first topic. Our first topic will be object method selection. And just take like a minute to maybe appreciate the meme that I put on there. Okay. So before we get started, we have to talk about static and dynamic typing, right? So we all know that Java is a language that is first compiled into machine code, and then a completely separate runtime system executes that machine code. So as a result, every single object in Java has two different types, right? We have the compile time type, which is sometimes referred to as the static type, and the runtime type, which is the dynamic type. The compile time type is a signed-on declaration, and it will never change, right? With the only exception of casting. However, casting can only change the compile time type for this object in the context of that single line. And the syntax is to the right. You would just wrap the new type in the parentheses and put the object name on next to it. And then the runtime type is a signed-on instantiation of that object. And that type is actually like the type of object that the box is being pointed at, right? The reference box is pointed at. And then errors can arise in both compile time and runtime. And the most common compile time errors are syntactical errors, right? Like if you spell something wrong, or if you have like some functions or variables that are missing. And then the runtime error would occur in like the non-syntax related situations, such as when you have like no pointer exceptions or something like that. And then we have to discuss this like a relatively special situation called dynamic method selection. So this would only occur when the methods are non-static, right? So like when there is not a static modifier on the method on the method signature. And the second condition is that the object must have a different compile time and runtime types. So if you look at the code to our left, we have an animal class. We also have a dog class that would extend animal. And at the bottom, we create animal A, and that is a new dog object, right? So in this situation, the compile time type for A is animal, and the runtime type for A is dog. And they have like obviously different types. And the third situation, or rather the third requirement, is that the runtime type overrides the same method that is found in the compile time type. So let's go back to the example. In the animal class, we have this big noise function that has implementation A. And in the dog class, you have the same big noise method with implementation B. And what happens when I call A.big noise is that it would actually goes into the runtime type of A, which is dog, and then we'll execute implementation B. Okay, so let's jump into one exam problem. On the top right corner, you can see like this is the general object map. You have a fingerprint class, you have a key class, and a skeleton key that extends key. And you also have a bio box class that extends standard box. Okay, so let's do the two problems right here. All right, right before we go over the solutions, behind me there's and also in the chat there's a Slido link where you can post any questions or just confusions, and then the staff right here will answer you live. So let's look at the first line, right? We have SB, which has compile time and runtime type standard box. And then when we call unlock SB on a K parameter, which has a type key, what's going to happen is that right, since the compile time and the runtime type is the same, the Java will actually go into the standard box class and locate the unlock method, and it will just run this UK implementation, right? And then we have SBBB, which has standard box compile time type and BioBox runtime type. In this case, we see that UK will still be run. And the reason is that when we look into the runtime type for SBBB, which is BioBox, this unlock method does not override the standard box unlock method, right? It overloads it instead of override it. So it will still run the UK implementation for unlock. Okay. Now we have 3 more problems. Maybe let's take 2 minutes.
If anybody wants the link, it's like.
All right, let's go over these 3 problems. Once again, with sb.unlock, we passed in a skeleton key object instead of a key object. And similar to the last situation, it would still select UK, right? Because like both types for SB are both standard box, and the unlock method in standard box would satisfy this requirement. So that would be the method that is selected and is executed. In the second situation, we see that UK is still executed for the same reason, that like the unlock skeleton key SK method does not exactly override the standard box unlock method. And finally, we have this BioBox BB object, and we see that like inside BioBox, you just have this unlock method that would take in a skeleton key, and this corresponding USK method would be executed.
Sorry, can you please re-explain why?
Should we answer questions, or should we encourage them like put it on Slido? I think if you have any questions, just post it on there for the interest of time. Yeah, sorry about that. So the next topic is going to be iterables and iterators. So on a high level, these are just 2 interfaces, right? For something to be an iterable, the only requirement that it has to satisfy is that like this object must have a corresponding iterator. And that's basically it, right? And then to be an iterator, you need there are 2 requirements. One is that like you should be able to tell whether the iterable on which that you're trying to iterate through has a next element in this iteration. And it's this has next method. And the second requirement is the next method, right? And like that method will actually return the next element in the iteration. And as I said, like both of these are interfaces, and they are generic over the type T, where T is the type of the data that is stored inside the iterable. Once again, iterables is the actual objects like array list that can be traversed through, and iterators are the actual objects that would traverse through the iterables. So let's look at this problem, vote iterator. And basically, this setup is as such, given an input int array, it would correspond to the indices of this array will correspond to a candidate, And the value at each index corresponds to the number of votes that this corresponding candidate received. And you want to implement an iterator that would be able to basically count the vote, right? So given this input, you would expect 1 to be outputted twice, 2 to be outputted once, and 4 to be outputted once. So let's look at this skeleton on how to implement the has-next method. On the right, there's like a little diagram that would hopefully give you some idea of how to do it. And let's take 2 minutes to do that. I'm not.
There's one main question. That
Yes.
A lot of people seem to ask.
Is there any chance that you guys can answer that? Or
Is on the reason why SBBB dot unlock K is equivalent, like the answer to that is that UK would run. The reason why UK would run in this case is because, do you mind if I go back to the slide real quick?
Yeah.
Okay. Okay, so so this one, the reason why the an SK is what again? Skeleton key. Yes. So the reason why we would run UK is because when we want to look for the method to run, we first need to look at during compile time, we first need to look at the standard static type of the actual object. And in that case, it's standard box. So we know we have to look for a method inside standard box. However, our parameter is skeleton key. And even though there is no unlock method that has the parameter skeleton key, it does have a parameter key. And because because skeleton key is a key, there is a relationship, we have to use the unlock key with the letter K. And because of that, during runtime time, what we would do is we would want to find a method inside the BioBox class that has the name unlock and has the parameter key, not skeleton key, just key. And since we don't have that, we know that UK would run as a result. Does that make sense?
But still, like building on top of that, so like for example,
Yeah,
BioBox.
pretty much what you
for
get a compile time,
SBBB.
it has to match at runtime.
But like in runtime, doesn't it do dynamic method selection and pick SBBB's unlock method in which it has the skeleton key parameter?
yeah. Oh yeah. Okay, so on the screen is going to be the solution for the has-next method. And basically the idea, right, is like we have so the num vote corresponds to like the current vote that this candidate has that this candidate received that has already been announced, right? So like if there are more votes that this candidate has, there obviously is a next element and it will return true. Otherwise, this for loop will basically like traverse through the entirety of the input array until it finds the next candidate with a ballot count. Right. And then let's take 3 minutes to implement the next method. Okay, so this is the solution for the next method. And once again, the main idea is that right, this if statement checks for whether every vote that this candidate has already been announced. If it does, you would move on to the next candidate, and then you would reset the non-vote counter, right? If there are still more votes to this candidate, you will be incrementing the vote, the number of vote that this candidate has announced for this candidate, and then you will return the candidate number, right? I hope that makes sense. Okay, so the next topic will be asymptotics.
Yeah. I need to go ahead and do a couple of things first. Well, first, let's leave it all here. Where's Wes?
I have printed this.
We might have to come back to it. I'll just.
Should I have some time?
Okay. We can skip asymptotics for now. We'll go
Alright.
to the next one. We'll
Okay.
go back to asymptotics later. The presenters currently.
And is it still have answer need?
Okay, now we're back to disjoint sets. Is that good?
Because it is
Okay.
a earphone.
Oh, no, so when you put it on there, it's gonna go into a certain box, and we got those labels. and we can,
Okay, so I can.
Right.
just put it on.
So disjoint sets. It's kind of exactly how it sounds. We have like, yes.
email, so you get the confirmation.
For
Okay.
afterwards, initialize the last day, and then like give it it's like initialize to like A and B. If B is a method that A does not have, and it's called X dot that method, does it compile or does it not?
It's not compatible.
So all the methods are not it's A, X, and B.
Yeah, in the case where it's like A, some name A is equal to new B. If you're looking for a method that's only in B, you're not gonna find it in compile. Yeah, you can do cast, yes.
Right. Yeah. So let's go ahead and head on to disjoint sets. So as the name applies, disjoint sets are like we have like these series of sets that are disjoints, and we can perform a couple different operations on them. The first being connect. So for any given input X and Y, we want to connect whatever the set that X belongs to Y. So like if X and Y are from two separate different sets, right, then we're going to union those two sets together. If they're part of the same set, then we don't really do anything. And then for is connected, it returns true if these two sets are in fact part of the same set, and false otherwise. So just an example, we have a couple of sets here. Each of these are going to belong to their own individual set. So A, B, C, D, E, F, G. And when we call like the connect method, right, what we'll do is that we'll take A and B and put them in the same set together. And then for B and C, we'll do the same thing. We'll put C into the set with A and B. And following up, C and A. And then we can draw an edge between C and A. But the thing is, C and A are already part of the same set. So for most implementation of disjoint sets, we don't really need to connect C and A since they're already part of the same set. So we can kind of just like neglect this edge right here. So next up, we do B and D, and then E and F, F and G. And then when we do a query to see like, is A and B part of the same set? Well, we have to try to find, well, for them to be part of the same set, there must exist some path between A and B. So right here on the left, you can kind of see that A and B, there is a path between them. So we can return true in this case. And then in the case of C and then D, we can see that there is a path between C and then D, because if we go through B, then we can get to any of the C or D in this case. So we'll return true. Same thing for E and F here. They're part of the same set, and there exists some path between them. So we return true in this case. And then for A and E, we can see that if we start at E and then we try to go like anywhere within that set, we can't really get to A anyway. So we'll return false in this case. So these are the 4 implementations that we're going to be talking about today. We're going to kind of walk through each one of them and their overall runtimes and see how does it compare to each other. So quick find is probably like the most straightforward way of being able to like implement this. And the general idea is that for every single set, we're going to represent it with some value. So this set right here, we're going to call it 4. And then this set right here, we're going to call it 5, and then 6, and so forth. And then so at the very bottom right here, these indices are going to represent okay, each individual node, and the value that's stored at that in this index is going to represent the quote unquote set that's belonging to. So for node 0, we can see that it belongs into set 4, and then for node 1, it belongs into the set 4. So when we want to do like a operation to check to see if 2 items are within the same set, all we really have to do is that we have to just ask, okay, 0 and 5, are you guys part of the same set? So if we take a look at index 0, it's in part of set 4. And if we take a look at, sorry if it's blocking it, index 5, right? We can see that it's part of set 5. So it will return false in this case. So what if we want to go ahead and do connect? Well, if we wanted to run connect, what we have to do is that, first of all, we're going to have to find the parent. I mean, not the parent, sorry. We're going to have to, we're going to have to find like the quote unquote like ID of like the element, the set ID that is. So since we're connecting 2 to 3, right? 3's quote unquote set ID is going to be 5, right? And then what we're going to do is that for every single other element within the other sets, right? So that set 4 that we're trying to join it to, we're going to take that number and we're going to copy it, and for every single 4 that we see, and we're going to paste it to every single element that contains 4. So here's what it kind of looks like side by side. And if we want to go ahead and like run some runtime analysis on this, right? To be able to find 2 elements, if they are just part of the same set or not. In other words, if we want to run connected, right? Then the time that it takes for us to run this operation will be constant, because all we have to do is look at the value at those indices. And then for is connected, in the worst case, if we want to run connect, in the worst case, we can think about like a new element that's being added to a set. And then this set all belongs into the same set. So what will end up happening is that we're going to have to take that value and we kind of have to like copy it to every single slot within that other set.
Yeah, in any way, why we do 5 at the P, but not 4?
Not 4?
Yeah, like when we connect to
2 or 4.
like why we all take it, not 4. Yeah.
Okay, so like usually you pick a convention, right? So when we call like connect 2 to 3, right? We say that we want to connect 3 to whatever 2 is pointing to. So like it's just a way to keep like you could technically do it the other way if you really wanted to, but usually for consistency's sake, right? We just usually say right. So just kind of summarize it up. Connected takes n time, and then is connected, it takes constant time. And then for quick union, now we kind of change it up a little bit, and what we do is that now we kind of want to build everything like from a tree. So what we're going to do is that for every single root node, we're going to represent that root node with -1. And then the value stored at each value is gonna represent the parent of that index. So for example, if we take a look at node 2, its parent is 0. And then if we take a look at this array representation, at index 2, we can see that its parent is 0. So just as a quick example real quick, if we want to call something like union 5,2, the first thing that we have to do is that we have to find the root of 5. So to find the root of 5, all we have to do is that we're going to take a look at the 5th index and see that, okay, there's a value of 3 being stored inside there. So now we need to do the same thing for 2. Now looking at 2, the value stored at index 2 is 0, and that represents its parent. And then now that we have that, again, sticking with the convention that we want to attach the first argument to the second argument, we're gonna say that we're gonna set 5's value equal to 2's root. So taking a look at 3 right here. So 3, this is the parent of 5, right? And then we're gonna overwrite that with 0 because that is the parent of 2. So now taking a look at them side by side, here's what it kind of looks like before and after. And then to run this connect operation, we can think about this in the worst case possible time. And that is, what if like we have like a spindly tree where like everything is like essentially like a linked list? Well, it'll take n time to traverse that tree. And as you can kind of see, like is connected kind of works in the same way. And for the remainder of the implementation, you'll see that the height heavily depends on, the runtime heavily depends on the overall height of the tree. So both of them will run in linear time. We can see that with this implementation, it does take up more time, but we're going to see later on that we're going to change this up a little bit and possibly run into some change up implementation to take into consideration like other factors so that we can actually speed up this process. And one of that process is weighted quick union. And then the general idea behind weighted quick union is that, okay, we had an issue of like a tree being like quote unquote spindly, right? So let's take a look at an example real quick. We have this set right here that's of height 1, and then this set over here of height 2. We can kind of see that if we connect this 3, if we connect this 0 onto this 3, what would happen is that, well, we'll increase the height of the overall tree, right? So that's not what we really want, right? We want to minimize the height of the tree to be able to increase overall runtime. So we take a look at if we actually connect this 3 to 0, then the height actually stays at 1. So the overall idea behind this is that we want to ensure that 2 tree creates a new tree from the smallest possible height. So we should always connect the smaller tree, in this case 3, to the larger tree. Okay, so going off of that, and if we take a look at this, we can kind of see that this is kind of like what we talked about earlier. We're taking the smaller tree, 3, 2, and we're connecting it to 0. And what we're doing here is that, sorry you guys can't see this one. It's just in a way, yeah. What we do is that at every single node, value right here, if it is a node, if it is a root, we're going to store how many elements are within the set. So taking a look at 0 right here, the number of items that are within 0 is 5. And we're going to negate it, and we're going to say -5 is going to represent. This is negative tells us that this is a root. 5 tells us the number of elements within this set. And then we can keep the same method for the previous implementation where like, okay, at index 0, at index 1, its parent is 0. And so by keeping track of how many items are within like this set, we can kind of see, okay, which tree should we connect to what tree? So if the left is smaller than the right, then we should definitely connect this smaller tree to the larger tree. The left to the right. So what is the overall runtime of this? Well, let's take a look at this example real quick. We have this disjoint set, and your job is to be able to come up with a series of connect operations that would increase the height of this tree. So go ahead, take like maybe 3 minutes to kind of think about that, and we'll go over it. Yeah, so for people on Zoom, I forgot I was muted. So like, does anyone have any, I just asked everyone if they have any clues about how to be able to accomplish this.
So take the next, 3, 2,
Mhm,
then 5, 3,
mhm.
and then you do 2, 3.
Yeah, that's exactly correct. So I'm just gonna kind of like go at this like a different way, right? So like let's suppose that we want to connect like just everything on the right hand side to left hand side, right? So what this will happen, what will happen is that we'll end up connecting everything to the 0 root, and the height of the tree doesn't really increase here. But earlier, you just said that if we connected 2 and then 3, and then 5 and then 3, now that we have like 2 different sets that are like relatively like the same size, when we call connect on them, then it will increase the height. And the reason why this is important is that now we kind of realize that in order to be able to increase the height of the tree by 1, we need to kind of double the number of nodes that is required. So by this process of requiring double the amount of input to be able to increase the runtime by 1, you can say that, okay, the height of the tree kind of grows logarithmically. And then so you can kind of see here that both connect operation and is connected runs in log time, because both of them kind of really heavily depend on the overall height of the tree. So now finally, path compression. And the big general idea behind path compression is that we have this weighted quick union as before, but now instead of like traversing up the tree and not doing anything in relations to keeping track of like where we've been, now what we're gonna do is that for every time that we go up the tree, we're gonna collect values. So when we call is connected 7 and 4, for every single value that we pass by, as we're trying to fetch the root node, we're gonna take that value and we're gonna assign it to the root node. So when I'm collecting new nodes on the left-hand side here, like 7, 6, and then 0, I'm gonna compress it so that they all go to the same root. In this case, 0. And then I'm gonna do the same thing on this side. Everything that I pass by, I'm gonna compress it down to 0. And it's all gonna connect to 0. And the reason why 5 here isn't really like quote unquote compressed is because like it's not part of the path between the node I'm looking at versus the root node. So both of them, we can see that because we do this kind of operation, we're kind of applying a log within a log within a log. So the more times that we call is connected, the more log functions that we kind of apply to the overall height of the tree. So you have a log of a log of a log, which for all intents and purposes, you can say it's constant time because that function grows extremely slow. All right, I'm go ahead and pass it on over to hashing now.
Hi, I'm Elena, and I'll be covering hashing. So first, let's talk about hash tables. A hash table is a data structure that maps unique keys to values, creating a key value pair. This is similar to a Python dictionary, but the way we implement it is in Java is usually with an array of linked lists. Each array index is a bucket, and each bucket points to a linked list. But actually, instead of linked lists, we can use pretty much any data structure like array list or even a tree. The Java implementation of a hash table relies on hashing, which is converting an element which can be a primitive value or object as an integer. By hashing, we can search, insert, delete elements in a hash table. A hash table has a load factor, which is the number of elements divided by the number of buckets. Here, the number of elements is n, and the number of buckets is m. So the load factor is n over m. You can think about this as the average number of elements per bucket. A hash table needs to be resized if the load factor reaches a certain threshold. So the way a hash table works is we first apply a hash function to an item in order to generate a hash code. Then the hash code is reduced to an index number. This is usually by modding the hash code by the number of buckets in the hash table, m. Then once we have the index, we go into the table and find that bucket with that index. Then we insert the object inside the bucket. For hash table, the insert method, we also want to check if the load factor has reached the threshold. And in that case, we want to resize. So we get the hash code by using a hash function. A valid hash function is deterministic, meaning that it always returns the same hash code for the same input. And equal objects have the same hash code. However, a valid hash function does not necessarily ensure that unequal objects have different hash codes, but it's something that we want ideally. In addition, a good hash function will also be uniform, meaning that it evenly distributes the items across all buckets. It will also be efficient, meaning that it runs in constant time. And unequal objects will have different hash codes. The default hash code method returns the memory address of the object. So as we said, a good hash function is uniform, meaning that it evenly distributes the elements. And this way we avoid collisions. A collision is having multiple items fall into the same bucket. If we have the number of elements exceeding the number of buckets, collisions are inevitable. There are multiple ways hash tables handle collisions. One way is with open addressing, which is not covered in 61B. But the one that we talk about in 61B is with separate chaining. In this way, each bucket points to a data structure, as we said, usually linked lists, to hold elements inside that bucket. So about the runtime of a hash table, the amortized or average runtime of a hash table is O1, constant time for search, insertion, and deletion. And this is maintained due to resizing, leading to few collisions. In the worst case, the hash table runs in O(n) time. If we use separate chaining, in this case, we have a bad hash function and all of the elements fall into the same bucket, creating one length n linked list inside that bucket. The resizing method in a hash table runs in O(n) time. Because the insertion method runs in O1, we call that insertion method n times to reinsert all the n elements inside that hash table in order to resize it and make a bigger hash table. So here is an example problem that we can try. It's from Spring 2018 Midterm 2, question 2A. So this question asks us to draw a hash table that is created by the following code. And an X list is a list of integers. And the hash table, hash code of an X list is the sum of the digits in the list. And two X lists are equal if they have the same length, they have the same values, and the values are in the same order. So we have this hash table for bucket hash map that uses external chaining or separate chaining, and it never gets resized, and it always has 4 buckets. Here we have this code, and the first element that is inserted is the key value pair xlist 1, 2, 3, and with the value cat, and then we have to insert the rest of the elements inside the hash table. I'll give everyone a minute or so in order to try this on their own. And I'll also take a look at the questions if there were any on Zoom. Oh. Yeah, and feel free if you also had any questions about hash tables up until this point. All right, now that we've all had a minute, is everyone ready to go over it? Okay. So we will go over the answers together. So as we said, the first value that was inserted was cat with the key 1, 2, 3. And in this question, it said the hash code is the sum of the values in the X list. So 1 + 2 + 3 is 6. And then we mod by the number of buckets that we have. So 6 mod 4 is 2. And that's why the first element was inserted in bucket 2. The second value is writing with the key 1, 4. And we got the hash code 5. And mod 4 is 1. So it was inserted in index 1. The second value is A with the key 5, and then we do 5 mod 4 to get 1. And here we have the hash table, which uses separate chaining. So this was inserted after writing in index 1. The next value we have is bool with the key 3, 4. 3 + 4 is 7, and 7 mod 4 is 3. So it was inserted in index 3. And we have the last value that we want to try to add, which is below, and it has the key 1, 4. But here we notice that below has the same key as writing. And as we said, a hash table has unique keys, so it cannot have duplicate keys. So instead of inserting below as a new element, we instead replace the value with the key 1, 4. With the new value below. So that's why it was, instead of writing here, we update it with below. And that's how we get our final answer. Does anyone have any questions? So someone asked on Zoom, is this a property of external chaining? So external chaining is using like a data structure inside each bucket in order to hold elements. So if we didn't use external chaining, we would instead, for example, put every element inside its own bucket in the linked list. So external chaining allows us to like insert two elements in the same bucket. So multiple elements in the same bucket. And here we have the example below and A, which are both inserted in index 1. And someone else asked, is the table drawn on the left for the spring 2018? Yes, this hash table. Oh, so the one drawn on the right, no, that's not a hash table. That's just a chart I wrote in order to clearly display all the values, keys, hash codes, and how we got the indices. But the final solution is just the one directly below the question. So the original hash table in the question with the red boxes there. So the way that we found the hash code for cat, so we notice here that the cat is the value, and it has the key with the X list 1, 2, 3. And in the question, it says the hash, it says X list is a list of integers, and the hash code of an X list is the sum of the digits in the list. So we have this X list 1, 2, 3, 1 plus 2 plus 3 equals 6. And so that's how we got the hash code. Yes.
How do we know to place the linked list that has like writing 1, 4 with the
Yeah, so we replaced the last value because we wanted to insert below with the key 1, 4, but we didn't reinsert it as a new element because we can't have duplicate keys. Yeah. Yes. Will we have a question where we'll need to implement the hash tables? Well, this was taken from a past midterm too, so I think that's a possibility. Yeah. Does anyone have any other questions? All right. If not, we will go to the next topic, which is trees.
Actually, we're going to cover asymptotics first.
Oh, we're gonna actually cover asymptotics.
Yeah. Okay. Where's Wesley? Oh, where Wesley go?
Yeah, I'm here.
Here we go. Okay. 1 second. I'm gonna go back to the asymptotic slides. Wesley, could you say something?
Hello. Hello. I can hear me.
Can everybody hear in the audience? Okay,
Can you
yeah.
guys hear me?
Yeah, they can
Okay,
hear.
cool.
Let me know when you want to change slides and I'll change for you.
All right, cool. Next slide. All right, so asymptotics is basically going to be about runtime. So it's all about how fast or slow an algorithm runs. So as you guys can see on the charts to the right, we have big O complexity charts. So this is basically a chart of all the runtimes. So we have our good ones, which is we have constant time and log n and sometimes linear. Our not so good ones, which is factorial, exponential, and quadratic. And we care about how fast an algorithm runs as n approaches infinity, because that's all about what asymptotics are. Sometimes a mistake students make is that they would input a value such as 0 or 1 and then try to evaluate the runtime for that. We don't want to do that because that kind of defeats the purpose of runtime. of asymptotics. Asymptotics is all about approaching infinity. So always input very large values for n. Okay, next slide. So we have three terms. We have big O, theta, and omega. So big O is upper bound. When we say big O, this basically means that a function can run that time or anything faster than that, which is, you know, upper bound. Omega refers to lower bound. So that is so the function can run anything that time or slower. And then theta is when big O meets big omega. That means a function will always run in that time. And a thing to note here is that big O does not refer to worst case, and omega does not refer to best case. So when we want to talk about best case and worst case, best case and worst case is only going to be that case, right? There's only going to be one of those best and worst cases. So we want to talk about those using theta. But when we're talking about overall runtime, we want to be using big O and big omega. Okay, next slide. Okay, so here's a quick example. So the thing about asymptotics is that we only care about the overall runtime. So we don't really care about any smaller terms or any coefficients. So here we have 9x squared plus 3x plus 14 times log x. So we only right now we only care about the biggest term, which in this case is the quadratic term, because this term is basically going to overshadow all of the smaller terms. So we don't really care about those. And we also want to ignore any coefficients because any of those also all go in the same class, right? So 9x squared would go inside the quadratic class. So in this case, this is going to be theta of x squared. Okay, next slide. All right, here's another example. So when you guys see iterative functions and you guys want to try to find the runtime of that, a good strategy is to make a table and keep track of the i's and keep track of the work per iteration. All right, so let's just go through this quick function. So int count equals to 0, and we have a nested for loop. So int I is equal to 0, int j is equal to 0. J is less than I, j increments by 1 each time. And then inside that for loop, count is going to be increased by j. And we see that inside, so count plus equals j, that's going to take constant time, right? Because, you know, addition operations such as that is going to take constant time. And we just want to keep track of every work per iteration. So when I is equal to 0, we can see that it's going to take 0 work. When I is equal to 1, it's going to take 1 work. When I is equal to 2, it's going to take 2 work. And we can see this pattern continues all the way until I is equal to n minus 1 and work is n minus 1. So once we have all the works per iteration, all we got to do is just add these up, right? So 0 plus 1 plus 2 all the way to n minus 1. And this is going to be equal to quadratic time based on a formula. So when you guys see a formula like this, so 0 plus 1 plus 2, this is going to be quadratic time, so n squared. Okay, now here's another example. So midterm 2, question 4a. So here's a quick runtime analysis. We have a remove index, which takes in an array, and this array is going to be infinitely long. So n equals the length of the array, and this is going to be infinity. But int I can be anything you want it to be. Okay, so I'll give you guys about like 1 or 2 minutes to figure this one out. All right, so let's talk about best case. All right, so best case is if I is equal to n minus 1, since I can be anything we want it to be. So in this case, the inside of the for loop executes only once, right? So for j is equal to I, so j is equal to n minus 1. And then that is going to be the only time when j is going to be less than n. So then we see that inside of the for loop only executes once. So this is going to give us constant time. That is our best case. And as you can see here, it's going to be denoted by theta. And worst case is if I is equal to 1, right? That's the smallest number we can input for I. And in this case, the inside of the for loop will execute n times or n minus 1 times. It's pretty much the same thing in this case. So then worst case is going to be linear time, theta of n. Okay, so next slide. All right, here's another one. So for iterations, we want to make a table. For recursion, we want to draw a tree structure. Okay, so let's go through this example. So we have a function which is recurse, takes an integer n, infinitely large, and that returns a helper function with n and n divided by 2. And when we go inside the helper function, n is going to be equal to infinity, and then m is going to be equal to n divided by 2. So we can skip over the if. So we can skip over the if statement right now because n is not less than or equal to 1. So we go inside the for loop, and we go through it. Actually, on next slide. Okay, so we go through it, and then we see that this for loop will give us log n divided by 2 times, and the smaller squares denote the size of n. Okay, and the bigger box inside represents the runtime for each call to a function. So the for loop execute has a log of n divided by 2 times. This is because we are multiplying I by 2 each time. Okay, so after that, we want to do a recursive call to actually 2 recursive calls. So helper of n minus 1 m and helper n minus 1 m. So same thing. And then this is going to give us this tree structure. So on the next level, each n is going to be equal to n minus 1. And then the runtime is still going to be log of n divided by 2 since m doesn't change. Okay, so m is always going to be equal to n divided by 2. And then as we can see here, there are going to be n levels if we keep going. Actually, next slide. Yeah, so there's going to be n levels if we keep going. And this is going to give us a sum of log of n divided by 2 plus 2 times log of n divided by 2 plus 4 times log of n divided by 2, all the way to 2 to the n times log of n divided by 2. And how did I get 2 to the n? Well, you guys can see here. So I'll denote the root node as the 0 level and the next node as the first level, right? So the pattern you guys can see here is that you can raise 2 to the level number, which will give you guys the coefficient. So 2 to the 0 is going to give you guys 1. 2 to the 1 is going to give you guys 2. 2 to the 2 is going to give you guys 4. And then you just keep repeating this process until you get to the very last level. And you guys can see here that n is going to be decreasing by 1 each time. So in the last level, it's going to give us 2 to the n. Okay. And now how do we simplify this sum? Well, we can factor out all of the 2 to the o, 2 to 1, 2 to the 2, all of those terms. And we can see that this is going to be a geometric sum, or some people might call it a dominating sum. This means that we only care about the last term because the last term is so big that we don't really care about the other terms. And in this case, we can see that if we add up all those together, we can see that it's going to be equal to 2 to the n. And then that's going to be times log n. So our worst case and best case is going to be equal to 2 to the n times log n. We have a question. So what n is equal to 1? What best case is equal to constant time? Yeah, so here's the thing. So n can't be a very small number. It can't be 1. We always want n to be going to infinity. So we always want to input infinity as n, because for asymptotics, the definition of asymptotics is as it approaches infinity. So if we just plug in 1 for n, then that just defeats the whole purpose of what we are doing, right? Yeah, so in the last question, we considered I to be 1. We didn't consider n to be 1. In the last question, we still considered n to be infinity, but we can change I because that's not what we're comparing the runtime to. All right, we're seeing it as n approaches infinity, not as I approaches infinity. Does that make sense? Yeah, just as long as n is approaching to infinity, just make sure that n is always going to be approaching to infinity. Yeah. Okay, next slide. Okay, so yeah, you guys can ignore the answers. Yeah, you guys aren't supposed to see that right now. But okay, so worst case, yeah, we can just go through it. So you guys can see that best case is linear time and worst case is quadratic time. So why is this? Actually, can you go back a slide? Okay, yeah, there you go. All right, so let's start with best case. Actually, let's go through the function first. So we have a function find, which takes in an integer target and an integer array. And this integer array is going to be infinitely long. So n is going to be infinity still. And this has a return call find target array 0n. And then we go to the find function. So integer target is going to be our target integer. Integer array is going to be our infinitely long array. Int low is going to be 0 and high is going to be n. Okay. So first we can just skip the if statement. You know, low is not equal to high. Low plus 1 is not going to be equal to high. We can skip it. So we go to int mid is equal to low plus high divided by 2. This is basically going to be the middle, right? And we go through the for loop, and we see that this increment I increments by 1 each time. So this is going to give us n divided by 2 work for this. Okay. Now let's go to the return function, the return statement. Return array of mid is equal to target. Our best case is going to be if this is true. If this is true, you know, for OR statements, if the first section is true, nothing else matters. We only care about, we just stop executing there. Okay, so best case is if array of mid is equal to target. In this case, the find function performs n divided by 2 work in the for loop, and we return true. So in this case, the for loop is only going to execute once. Okay, and n divided by 2 simplifies to n in this case. So that was our best case. And then next slide. All right, now let's go to the worst case. So our worst case is if array of mid is not equal to target. So in this case, that statement is always going to be false. So now we want to execute our recursive calls to find. All right, so let's draw a tree. So the first node is going to be n divided by 2. And then we can see that the statement will give us this thing, will split the list into 2 halves. Okay. So low mid, that's going to be 0 to n divided by 2. And then mid to high is going to be n divided by 2 to n. Okay. Now we try to execute the for loop for these, and we see that I is still going to be equal to 0. So it's still going to be 0 to mid. That's why the left and right are not equal, because the mid for the right hand side is going to be 3n divided by 4. The left hand side is going to be n divided by 4. So then we find those runtimes, and we find that it's going to be n divided by 4, and then 3n divided by 4. And then we just keep going, and then we have this nice tree structure. So n divided by 8, 3n divided by 8, 5n divided by 8, and then 7n divided by 8. And then we can keep going, and then we can see that our summation becomes n divided by 2 plus 2n. So we're adding up all the runtimes in each level. So n divided by 2 plus n plus 2n plus 4n plus all the way to n divided by 2n. And this is going to be equal to 2 to the 2. This is going to be equal to quadratic time. And so how do we find the last term? Again, this is all about finding patterns. So one pattern is basically going by levels again, or oh, okay, yeah, okay, okay. Give me a second.
As Wesley is muted, does anybody have any questions on any asymptotics? Yes.
Okay, sorry about that. I'm back.
Oh, never mind. Okay.
Yeah. Okay, so how did I find that? Actually, give me a second. Okay, so one way you can find it is by finding a pattern between work and the size of n. Okay, so we can see that the size of n is going to be divided by 2 for each call or for each level. So first level we have n, so n is going to be equal to n, right? And then our work is for that first level or the 0 level is going to be n divided by 2. Now we keep going. The next level, work multiplies by 2, n is going to be divided by 2. So we can see this pattern. So we're just going to keep dividing n by 2 until it gets to 1. Yeah, we're going to keep dividing n until it gets to 1. And then we're going to keep multiplying work until it gets to n divided by 2. Or I'm sorry. So think of n divided by 2 as 1/2 times n. So think about the coefficient in this case. So first level, we have a coefficient of 1/2 and work of n, and n is going to be equal to n. So n and 1/2. And you guys can see that for every level, the work is going to be, the coefficient of work is going to be multiplied by 2. It's going to be multiplied by 2 each time. So 1/2 to 1 to 2 to 4 all the way to n divided by 2. So that's how we get the n divided by 2 times n. And we can see here that if we factor out all the coefficients, we get a dominating sum again. So 1/2 plus 1 plus 2 plus 4 all the way to n divided by 2. And in this case, all we care about is n divided by 2. So n divided by 2 times n is going to be basically n squared, which is going to be quadratic time. So that is going to be our worst case.
All right. Thank you, Wesley.
Okay. Yeah.
Yeah. Okay. 1 second. I will just. Okay. You had a question earlier. Well, what was the question? This one? Or the one before? Maybe it's the one before.
Yeah. Oh, yeah. My question for this one is that, so it says that the height is n level, but the answer ended up being like 2 to the power of n log n. I understand why like both of those things come with together, but I don't understand what's the significance of it being n levels long.
The reason why we would consider it being n levels long is because when we go ahead and try to sum up all the runtimes at each level, what we end up getting is this kind of sum right here, as Wesley pointed out. So as we noticed at the top, it was log n divided by 2. And then because we had another level in which the work at each node was the same, we know that it's 2 times log of n divided by 2. And then we know that, and since we know we're going to keep going down n levels, and we notice that the length of each like level grows by 2. What's going to end up happening is that we know that our biggest term is going to be at our final level, which is our nth level. And then we know that there are 2 to the n nodes. And because of that, because we know that the work at each one is log to n divided by 2, we know that our like largest term is going to be 2 to the power of log n divided by 2. However, because this is asymptotics, we ignore any kind of constants. So what we do is just say that our runtime is our largest term represented asymptotically, which is 2 to the power of n times log n.
I was thinking it's going to be n log n. Can you explain how it would be n log n?
N log n, pretty much what would happen is let's say we keep having something like log n divided by 2 at each level. But instead, rather it splitting off into 2 levels, it would just be like consecutive one time. For those on Zoom, hopefully you guys can see what I'm about to write here. So right now we had something like this. Log n divided by 2. Can you all see this properly?
Yeah.
Okay. See, right now this is what we were working with. Now let's say if we decide, if we know that we're going to be working with n levels, let's say we just go with like one sort of order down. So pretty much just becomes log n divided by 2, log n divided by 2. And then because we have n levels of the same amount of work per node, what we're end up going to get is n times log n over 2, which represented asymptotically is n log n. Okay, yeah, yes. Okay, well, are you referring to like the first call to helper in recursive calls to helper within helper? Well, the thing is, we're gonna already represent our first call to helper at the top, at like the top. So if I have a so at the top, like or top row is just going to be that first call. And then what's going to happen is that we're only going to be working recursively. We're not going to call recurse at all. We're only calling helper. And so what ends up happening is that then we just keep on splitting helper. We don't keep on splitting helper. And so that's why we split by 2 instead of 3. Yes. Yes. Any questions before we move on to trees? Okay. Yeah, we'll go ahead and yeah, of course. Here we go. Do you want to change screen?
Yeah.
Okay, I'll do that.
Let's resume. Give us a moment, everyone. We're trying to switch screens to an iPad.
I have another. We can just do airplane.
Oh, yeah.
Because I think both of us will be connected to the same. So, sorry, 1 second.
Whoa, what I had they've never done this before.
Okay. So, let me turn on. I got this.
I forgot I had it for.
It's okay.
That's so weird.
Oh, here we go. Am I connected to Edgero? Yes, I am. Okay, so screen mirroring. Here we go. What?
Oh, wait, no, it's PC. Wait, what? Nah.
It was supposed to be Zoom PC, so we'll try one more time.
I got another idea real quick. Let me see if I can.
We're really sorry about the delays, everybody.
I'm trying my iPad.
Huh?
I'm trying my, like, why don't you just
Oh,
join
join
Zoom
it here.
from-
Yeah, I'll do that right now. I have to think.
Okay, I got it. Yeah.
Can everyone in the Zoom hear me? All right, I'm going to take that as a yes. So for our first topic, we're going to be going over trees really quickly. So there are a couple of rules that trees follow, and they are, if there are n nodes, there are n minus 1 edges. The second rule is that there is exactly one path from every node to every other node. And the third and last rule is that the above two rules mean that trees are fully connected and contain no cycles. So a cycle is a set of edges that start at one vertex and then go all the way back to that same vertex without any repeating edges. So some terminology is that a parent node points towards its child. The root of a tree is a node with no parents, and you can consider it the top of a tree. And a leaf of a tree is a node with no child nodes, and these are generally at the bottom of the tree. So to demonstrate, in this tree over here to the right, the root would be over here, the leaves would be over here. And we can see that this is a valid tree as they are 5 nodes and 4 edges. Moreover, there's also no cycles in this tree, so it's perfectly valid. Are there any questions on trees before we continue? Okay, moving on. So now we're going to go over binary search trees. So binary search trees are data structures that allow us to quickly sort through our access elements in some sort of sorted order. They have several very important properties. The first one being each node in a BST is a root of a smaller BST. Every node to the left of a root has a value less than the root, and every node to the right of it has a value greater than the root. So pretty much we can see over here, let's say, let's look at this value 6. We can see that all the values in the left subtree are less than 6, and all the values in the right subtree are greater than 6. Can do this again if we take a look at this value 3 right over here. As you can see, it has one left child 2, which is less than it, and it has one right child 4, which is greater than it. Moving on, so we're going to go over an operation on binary search trees, which is insertion. So new items in a BST are always inserted as leaves. So here we're going to insert the 2 node, and we have to follow the 3 rules that we discussed earlier when inserting in nodes. So if we want to insert in 2, we're going to start at this 5 node over here. And since 2 is less than 5, we're going to go to its right. And now we're at the 3. Since 2 is less than 3, we're going to go to its left. And now we're at the 1. And since 2 is greater than 1, we're going to insert over here because there is no node to the right of 4 originally. So you might be wondering, what happens if we try to insert a node that is already within the tree? For example, let's say we try to insert a 7. Well, then in that case, nothing will happen. So this means that a BST cannot contain duplicate nodes. So for deletion, there's multiple different cases, and the easiest case being that the node that we're deleting has 0 children. So let's say we want to delete 0 over here. Well, that's easy. We can just get rid of it. And let's say we had to delete the 9. Well, we can just get rid of it, and it still follows the properties of a perfectly valid BST. Now, the second case is that we have 1 child, which is a little bit more complicated. So let's say we want to delete the 2 over here. Then what we do is we delete the node, and then we'd promote the node's child to connect to the node's parent over here. Let me draw that a little better. Like that. So that is deletion for 1 child. And then the final type of deletion is when we have 2 children. And this is a little complicated. So there's 2 different ways of doing this. So either we replace the node with the largest descendant on the left subtree or the smallest descendant on the right. And we can find the largest descendant on the left by looking at the furthest node right in the left subtree, or we can find the largest descendant on the right by looking at the furthest left node in the right subtree. So let's take a look at a deletion operation, and this time I'm going to be trying to find the largest descendant on the left and replacing the node with it. So we're going to delete the 5 over here, and then we're going to look at the largest descendant on the left subtree, which is right over here. And taking a look at it, the largest descendant is 4. So we're going to get rid of the 5 and then swap it over here with the 4. And as we can see, this is a perfectly valid BST, as the elements to the right of the 4, or the elements to the left of the 4 are less than it, and the elements to the right are greater than 4. Are there any questions so far? Yeah. Oh. Okay. Thank you. Does anyone else have like any questions or concerns? Let me check the chat real quick. Nope. Okay. So let's go over the asymptotics of a binary search tree. So our best case is when we have a bushy binary search tree, which means that pretty much every node has a left and right child. And this means that the height of this tree is going to be log of n. And that's why we can get these search, insertion, and deletion operations within theta of n time. Now, our worst case is when we have a spindly BS tree, which kind of looks like a linked list. And essentially, let's say this list is of size n. Then if we want to search for if an element is within it, then in the worst case, we'd have to go all the way down this list, which is a theta of n time. And same with insertion and deletion. So this means that the overall runtime for a binary search tree using our best and worst case is going to be big O of n. Should not say omega of n, because technically we can insert an element faster depending on how the tree looks. Are there any questions on the asymptotics of a BST? Yeah.
So the asymptotics are basically each of like proportional to height. So like the taller tree has higher asymptotics.
Yeah, so a taller tree will run slower. That's exactly it. And that's why a BST runs faster if it's bushy, because its height is less than a spindly one. Any other questions? Nope. Okay, so moving on to balanced search trees. So there's two different types of balanced search trees. There's 2-3 trees and there's 2-3-4 trees. And they both serve a similar function to binary trees while ensuring that it's going to remain bushy. And this means that all leaves are going to be the same distance from the root. So essentially, it's going to be like log n of length to travel from a leaf to the root. So the difference between these two data structures is that a 2-3 tree can either have 2 or 3 children max per node. The maximum size of a node is 2 items. And a 2-3-4 tree can have either 2, 3, or 4 children per node, and the maximum size of a node is 3 items. So pretty much a node can have either 1 or 2 items if it's a 2-3 tree, or it can have 1, 2, or 3 items if it's a 2-3-4 tree. So you might be wondering why binary search trees, and that's because they solve the problem of insertion affecting the height and therefore the performance of a binary search tree. So take, for example, let's say we insert 1, 2, 3, 4, 5 in order. Well, then we end up with this spindly BS tree over here to the left. And this has a height of theta n if we keep on inserting more and more elements. And let's say if we want to find the last element within this spindly tree, that would take us theta of n time, which is not that great compared to a bushy tree, which would take us theta of log n time. So that's when the 2-3 tree comes in. Pretty much the height of a 2-3 tree is always going to be log of n. And this is because every leaf is the same distance from the root of a 2-3 tree. Any questions so far? Yeah.
like what will happen if, like, for example, we have like 1, 2, 3, 5, 6,
1, 2, 3, 5, 6.
and then we cannot be inserted as in the middle.
So the order is going to be 1.
Oh, never mind. Okay, never mind.
Yeah, the properties of a BS tree allow you to insert any node as long as if you're not inserting a repeated node. So it's the same as a binary search tree. So let's say if a 2 is already in this BST, if we try calling insert on 2, nothing would happen here. Does that answer your question? Okay, got it. So moving on. So we're going to talk about inserting into a 2-3 tree. So when inserting into a 2-3 tree, we're going to first insert into an existing leaf node according to the binary search tree rules. So pretty much this means that like if a node is less than like the root, we're going to want to insert on the left-hand side. If it's greater than the root, we're going to want to insert on the right-hand side. And if it's equal to the root, it means that the node is already within the 2-3 tree, and therefore we don't do anything. And then second, if necessary, we're going to push the middle element up and split the node. So we split the nodes after inserting, and we only split when there's 3 elements in a node. And pretty much when there's 3 elements in a node, we call it like overloaded or overcapacity, and then we push it up. So here I have an example. So we're going to insert 5 into this tree, and it's going to first be inserted into this middle node right over here with a 4, 5, and a 6. We notice that there's 3 elements within this node, and therefore we have to push up the 5 and then split the 4 and the 6 into 2 children. So as you can see here, the 5 gets pushed up, and then the 4 and the 6 become 2 children within the tree. Does that make sense? Got it, great. So as you can see, we have to do this one more time here because our new root has 3 elements. So we have to push the 5 up, and that turns its children into 3 and 7. And then we see that all the properties of the 2-3 tree are met. So we are good to move on with the insertion. So when inserting into a 2-3-4 tree, it's pretty similar to a 2-3 tree. So first we're going to insert into a leaf node according to the PST rules. And when traveling from the root to the leaf, if we see any nodes at capacity, i.e. 3 items, then we're going to push the middle node up, and then we're going to split, and then we're going to insert our node up here. So for example, if we want to insert 7 into this tree over here, we're first going to follow the rules of the binary search tree. So we see that 7 is greater than 3 and less than 8. So we're going to want to insert 7 into this node over here. However, we notice that it's at capacity. So first we're going to push up the 5, and that sends the 5 up to the root. And then we're going to insert the 7 into its appropriate spot, which is in the same node as 6, because 7 is greater than 5, but less than 8. Any questions on this? Okay. Sounds good. So now we're going to be going over red-black trees. So red-black trees / left-leaning red-black trees are a representation of B trees that we use because it's easier to work with in code. So they're the same thing. One's just a bit easier to write down for programmers. So a red-black tree is essentially a BST, but we color a branch red to indicate that it's in a stuffed node or a node with more than 1 element. And pretty much the path from the root to any leaf will see the same number of black branches, which means that it's log n to travel through from the root all the way to a leaf, no matter what. So below we have 2 different representations of red-black trees, one for a 2-3-4 tree and another for a 2-3 tree. So the way that I like to see it is that like if we have red branches, they're essentially going to be part of the same node. So right over here is going to be the same node. Over here in the 2, 3, 4 tree, it kind of represents this node over here, and the children are also replicated over there. As for looking to the right over here is another node, which is going to be the 5 and the 9. And the left-hand child will be A, which is going to be the left-hand child over here. The middle child will be the right-hand child of the node with the red edge. And then the right-hand child will be the right-hand child of the parent. Does that make sense, or is that a little complicated? I know that there's a lot of like wording. Okay, sounds good. So continuing on with left-leaning red-black trees. So LLRBs are a red-black tree, but we add an additional rule. So nodes with red edges can only be the left children of their parents. So for example, if we have a left-leaning red-black tree that looks like the pencil stopped working. Give us a moment, guys. The pencil stopped working temporarily. I should have sworn. Okay, we are back. So pretty much if we have tree that looks like this, it's not appropriate because pretty much nodes with red edges can only be the left children of their parents. However, we have a node with a red edge that is the right children of its parent. And we're gonna go over a couple operations that help us fix a tree like this in a couple moments. But before that, I just want to point out again that left-leaning red-black trees have a 1-to-1 mapping with a 2-3 tree. And we can see this by like pretty much making circles around any node that has a red edge and putting that together. So for example, this is represented over here. The left-hand side is represented over there. The middle side is represented over here. And finally, the right-hand side is represented over here. Okay, so inserting into a left-handed red-black tree. So there's a couple rules to follow. So we're gonna insert the item as a new leaf node, but we're always gonna color the edge that's pointing to it red. And then after that, we're gonna follow these rules. So, okay, the first one is rotate left. So if we have a node and it's pointing and its right-hand child has a red edge, then we're gonna make a rotate left rotation. So pretty much we're gonna set B to be the new parent here. And then its left-hand child is gonna be A. And then we're gonna set this child over here to be the right-handed child of A. And then we can keep the D as the right-hand child of B. For rotate right, pretty much if we have two sequential left-hand children, then we're gonna rotate to the right like this. And we're gonna make B the new parent, and it's gonna have two red children, D and A. And then for the final operation, we're gonna have color flip. So if a node has two red children, then we're gonna set those children both to be black, and then we're gonna set that node to be a red child. So pretty much we have two red children as indicated by these arrows over here. And then we're gonna set the arrow pointing it to be red after we set the two children to be black pointers. So quick question to y'all. After doing this one rotate right operation over here, is there anything else that we have to do after this? Or is this a valid? Yeah, we have to perform color filling. It's great. So, okay, quick example on LLRB insertion. We're gonna insert nodes as red, and we're gonna insert them pretty much in the same way as we insert for a binary search tree. So here we're gonna insert 1. 1 is less than 13. So we're gonna go to the right, and then 1 is less than 4, and there's a null here, so we can add it and create a new node. And then let's say we want to add 23. We're going to do the same thing over here. 23 is greater than 13. 23 is greater than 20. And then you're going to create a new node with a red pointer. However, we notice that because we have a red pointer to a right-hand child, we're going to need rotate left, and then we get the structure over here. Then let's say we insert 9. 9 is less than 13, and 9 is greater than 4. So we're going to want to insert over here. Because we have a node with 2 red children, we're going to color flip, and then there's that. So quick summary of red-black trees is that we have a couple of balancing operations if there are certain conditions to do. So if a node has 2 red children with red, or has 2 children with red edges, we're going to perform a color flip. If a node has a right child that has a right edge, then we're going to perform a rotate left. And if there are 2 consecutive red nodes with red edges, we're going to perform a rotate right. And pretty much the only other important thing on the slide is that search, add, and delete operations happen in log n time for a red-black or any balanced search tree. And there's some more practice here on the slides, but for the sake of time, I think there's another topic that we have to cover really quickly. And there's also more stuff in traversal too.
Okay, so nice. We are kind of tight on time, so it's totally cool if you do have to leave. Totally fine with me. But we will be here. Just going over heaps and priority queues. Should take no longer than 15 minutes, so if you want to stay, feel free. Can I zoom? Oh yeah, I can. All right, well, that's a little nice meme for you guys, but we don't got time to read it. Anyways. So what is a heap? A heap is essentially a specified it's a specific tree structure that maintains this one thing which we call a heap property. What is a heap property? Well, in this case, we're going to be dealing with min heap. There's min heap and max heap. But in min heap, essentially all children of a given node must be greater than my node. Does that make sense? So the root of a tree or a subtree is the minimum element in that tree. And we can see over here, 1 is going to be less than all of the elements below it. And same with this subtree, 2 is going to be less than all of its elements below it. And again, with this 4. There you go. There's a little description on what a max heap property is. So don't be surprised if you see it on a test. You should be prepared to deal with max heaps. Great. So how do we represent heaps in Java? Well, essentially, we just put them into an array and we set a couple of rules for indexing. Let's zoom out just a little bit. There you go. So why is that first or the 0th element x'd out? Well, essentially, we have to have this in order to be able to index through with these rules. Oh, before we get to those rules, though, look at the array. I'm not going to give out any hints because there's not many hints to the point where it gives out the answer. But what type of tree traversal is this? Look at the order in which the elements are stored in the array. Feel free to shout out or spam it in chat. Close. Well, it's gonna be level order. Yeah. Essentially, if you look at it, if we traverse this tree in level order, well, then we get the array. That's not too important, but I just wanted you guys to know that. Anyways, how do we get a parent of a given node? Well, choose a node, find its index, divide it by 2, round down if you need to, and that's its parent. Let's take a quick example. So right here, we're gonna try and find the parent of the node with value 5. We're gonna divide the index by 2, which gives us array of 2. And that value is 2. Notice how the value 2 is the parent of the node with value 5. Very simple. How do we find children? Well, there's the formula right there. You multiply your given index by 2 for the left child, and multiply by 2 and add 1 for the right child. Now, does anybody want to take a guess as to why we can't have that 0th element filled in with a given value? The formula. Yeah, but for simplicity's sake, you see how clean the formula is, right? Divide a given element by 2 or multiply or a given index by 2. So let's say if I wanted to try and find the child of something in the 0th index, you're going to multiply that by 2 and still get 0. So that's why we don't have an element in the 0th index. Questions so far? Cool. Feel free to interrupt me if you do have them. Let's go over insertion. So here we have a min heap, and we are going to insert 1. Go ahead and take literally 30 seconds or so, run through it mentally or write it down, try and work through this. Okay, I'm going to go ahead and go over it. So essentially, how we're going to start is we're going to insert this node in the bottommost level on the leftmost element. In this case, that's going to be right there. Notice how this does not, this does not work with our min heap property, right? 1 is less than 6. So we have violated that. Okay, let's fix it. What are we going to do? We're going to do something called bubbling up, in which we compare it to our value right above it. And let's do that, which is over here. We notice that 6 is going to be greater than 1. So we're going to swap those 2 elements. There we go. And we notice again that this tree isn't isn't satisfying our min heap property. So what are we going to do? We're going to swap 4 and 1. We're going to look at its parent, see if it's greater than. If it is, swap. Okay. And now we got our pretty little tree with 1 fully inserted. Any questions? Here's your formula right over here to insert. Cool. Deletion. Go ahead and delete the root node. Take 30 seconds, work through it mentally. All right. So what are we going to do first? Well, we're going to find our root node and remove the root node. And we're done. I'm kidding. You guys are supposed to laugh. We got to switch it with our bottommost level and our rightmost element. There we go. Notice how we removed the value of 1, swapped it with the value at the bottommost level, rightmost element. Great. Is this a valid min heap? No, right? The values below 6 are not are smaller than 6, right? And so let's go ahead and do something called bubbling down. We're going to compare it with the smallest child of 6 and swap it. There we go. Where is it? Is this it? Yes, there it is. We compared 6 with 5 and 4, chose the minimum of the children and swapped it. Great. And finally, we noticed that 7 is going to be greater than 6, so we now have a valid min heap. Pretty simple. If any of you guys want to write that formula down, take 20 seconds, or not 20 seconds, take a little bit, but write it down. And we're going to hop into a pretty fun practice problem. And then we're done. Yes.
Heaps are longer. Heaps are like all bushy, right?
Yes. Yes, they will be. They will always only have 2 children max. What's up?
So whenever you can have 2 children, it always gives you 2 children. Like for each node.
Not exact. There will be times when sometimes we will only need to have 1 child, but usually that child is like left leaning. So for
Yeah.
example, if we were to start a new row and we were to have like 1 child all the way on the left,
Yeah, but
that's
like,
the only.
yeah, but like 2 children as long as you can't have.
Yes.
Yeah, so this is also a valid min heap right here.
Yeah.
As long as it's always going to be a left-leaning balance tree. Great. Let's go ahead and get started with our final practice problem. If that is too small to read, yell at me and I'm going to read it out anyway. The main thing that you need to know is that x is going to be greater than y. Other than that, we have no clue what all of the other elements are. They can be equal to each other. They can be greater than, less than. All we know is that it maintains a min heap property, and there can be duplicate values as well. So go ahead and take 2 minutes, maybe 3 for A and B. do like 30 more seconds. Okay. Hope that wasn't too bad. But let's go ahead and do A. We'll start from the topmost answer rows and go from there. So we notice that the first one asks us to compare X and the grill. Okay, so let's see what we know so far. We know that Y is going to be less than X. Very simple. We also know by min heap property that the grill must be less than or equal to Y. Let's do G for grill. Questions so far? Cool. What does this mean? Well, we can set up this inequality just like this. Oopsie. This tells us that X can only be greater than the grill. None of the other possibilities, well, are possible. Does this make sense? Great. So we can go ahead and fill in that one. I'm going to go ahead and get rid of, oh, that's not. There we go. All right. So far we know now that Y is going to be less than X. And we know that the grill is going to be also less than X. So let's figure out this next row. We know that the lemonade must be, oopsie, nope, that's the other way around. Oh, wait, yeah. We know that the grill must be less than or equal to the lemonade by min heap property. And we also know that the grill also must be less than X from before. What does this tell us? Feel free to shout out. What does this tell us about the, oh, by lemonade, I mean the cocktail, by the way. Sorry, if that wasn't clear. What does this tell us for the relationship between X and the cocktail? Absolutely nothing. That's exactly what I wanted to hear, right? We only know that both of these things are going to be greater than grill, but we don't know how the lemonade / cocktail is going to be related to X. Great. So let's go ahead and fill in these guys. All right, and let me just clear some space. Great. By min heap property, we know that Y is going to be less than or equal to the can. The can is that can looking thing. Sorry, I can't help you out there if you don't know what the can is. But it's the same situation as last time, right? We know that essentially, sorry, this, and we know these three values, right? And we can't relate X and the can through Y in this case, because they're both going to be greater than Y. Great. So that means that we have zero clue about the relationship between these two. Questions so far? Cool. And finally, let's move on to B. Let me just clear some space over here. Again, we know that y is going to be less than x. Any guesses for y's relation to the dinosaur? Bingo. A min heap only guarantees that the elements below a given node are going to be greater than or equal to. So by that logic, the dinosaur has to be, or y has to be greater than the dinosaur or equal to, because there can be duplicates in this min heap. Great. Tractor. Guesses for tractor? And why not?
Both, the only thing you know is that they're both greater than barbecue thing,
Mm-hmm.
and barbecue thing does not really, and like the value of y and the value of tractor can be completely different as long as they're both greater than barbecue.
Exactly. I'm just going to repeat that loudly for also the Zoom people. We only know that y and the tractor are going to be greater than or equal to the grill. Does that tell us anything about y and the tractor? No, they can be, they're absolutely independent of each other. So we're going to fill those guys in. And finally, the last subpart of this entire review session. Let's kill it with excitement. Guesses for the last part? And why less than? So, say that one more time. The balloon, okay, the balloon is going to be bigger than x, yep. And y is less than x. Does that make sense to everybody? All right, so I'm just going to scroll down and show you guys all the answers. There we go. And thank you so much for coming. And oh, the last slide, yep. There you go. You guys got this.
Out of all of you, please fill out the survey. We really want to for like future semesters. So
Yeah, repeat the last one.
please fill out the last. People online, please fill out the survey.
All right, I'm going to repeat the last part really quickly for somebody on Zoom. Let's do it. Let's clear some space. All right, so that x must be less than or equal to the balloon, right? Balloon. We also know that x is going to be less than y. Let's combine these inequalities. So we're just combining these two equalities over here. And this big one, we notice that y must, there's no much room. Let's see. This means that y must be less than the balloon, because y is less than x and x is also less than the balloon. Hope that was helpful. Of course. There we go. All right, good luck on the midterm, y'all.